I think we can start. Thanks a lot for joining this tinyML talk. My name is Gianmarco Iodice. I'm a tech lead for the machine learning group at ARM, and also the chair of the tinyML global meetups. Today, I have the pleasure to host this session where Danilo Pau and Fabrizio Aimone will talk about the suitability of forward-forward and PEPITA learning to MLCommons-Tiny benchmarks. So before the presentation, just a bit of housekeeping. But first of all, I must thank all the strategic partners that are making these tinyML events possible. And here I'm going to list them: AZIP, Analog Devices, Arduino, ARM, BrainChip, Agent Pulse, Efficient, Grainwaves Technologies, Grovity, HiMax, IBM, ImageMob, Infineon, Inaterra, Microsoft, Not AI, NXP, Pauling Technology, Kixo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, STMicroelectronics, Synaptics, Syntiant, and TDK. Again, it is a great pleasure, honestly, and privilege to have these strategic partners that are making our events possible. Not just this, but also the other events that the tinyML Foundation is organizing in person and virtually. So global meetups. So we are a very big family, a family that is growing in terms of members. We are almost there to 17K members in 49 groups. We are almost there also for the first milestone, which is 50 groups worldwide. So this for the meetup, but also the LinkedIn community is growing. We have 4K members there and 13K followers. What I really recommend also to be always updated about our events and news on tinyML is to subscribe to these groups. So, but it does not stop, the learning does not stop here. It does not stop at the meetup. It does not stop on LinkedIn. There is also a YouTube channel where you can learn certainly more from our previous sessions, our tinyML talks. All the tinyML talks are recorded, including this one, which will be available tomorrow. And certainly the YouTube channel is the best place to learn, even if you don't know anything about tinyML, because there are presentations that cover any levels from beginners to very experts in this field. We already have more than 10K subscribers with, well, over 600 videos. So certainly this is the place that you should subscribe to have updates and notification about new videos. So tinyML Asia Technical Forum is approaching very fast because the 16th of November 2023, the tinyML Asia Technical Forum will be hosted in person in Seoul in South Korea. So if you have the chance to go there, so certainly this is an event that you should not miss, because you're gonna listen presentations about cutting-edge technologies and developments in tinyML from the Asian community. So here there is a link to learn more, including the QR code. Another thing I want to remind is about the 2023 AAIA technology report of Wevolver. So this is certainly an article that you should download if you haven't done yet, because you can discover the state of the art about machine learning on edge devices and tiny edge devices like microcontrollers, for instance, and other important devices and memory constrained devices. So already quite a lot of people have downloaded this report, so I recommend also in this case to download it and to learn from the experts about how this technology is growing and evolving. And to introduce the first speaker, also a friend and also a person widely known in the tinyML community, which is Danilo Pau. So it's absolutely a pleasure. Danilo, graduated in Politecnico di Milano, but is absolutely his background has been in the multimedia architectures, and he worked on memory reduced HTML hardware design. So he has a lot of experience in video memory reduction like MPEG-2. But as you're probably aware, Danilo is also the person who is driving this on-device learning on microcontrollers and also the on-device learning presentation. So it's absolutely a great pleasure to have you here, Danilo. And Fabrizio Aimone. Aimone is currently pursuing a bachelor degree in electronics engineering at Politecnico di Milano. He's also intern at System Research and Applications Department of STMicroelectronics, where he's studying solutions for on-device learning in the domain of time devices. His research interests focus on reducing memory usage and computational complexity of AI algorithms and exploring alternative learning rules to backpropagation. I think we're ready for your presentation. I'm looking forward to learning more from you. You can share your screen, Danilo.
First of all, thanks a lot, Gianmarco, for a very nice introduction, and it's a real big pleasure to have the opportunity to share what is latest efforts between me and Fabrizio Aimone, which is connected about an interesting topic. And the topic is going beyond backpropagation. I think it's time to really try to understand if this is a way to go, especially for tiny machine learning devices. And there are some perspectives which are nice to at least start to consider. And if you have questions, please let's share the questions as soon as you can. Fabrizio will be available to help me and support me in going through all of them. So, and he will lively answer them. So first of all, what is the agenda? What are the main topics I'm going to cover? Let's review a little bit why backpropagation is so important and widely used, and what are the implications of using such a workload. And then why do we need forward learning? Some very maybe trivial consideration, but there are strong argument I think we need to consider. And then a couple of approaches that appeared in the last very few years, which are known as forward-forward and PEPITA algorithm from Hinton and Della Ferreira in Italy. And so we need to understand a little bit why this seems a needed departure from backpropagation workloads. And then let's also share a question that is behind the title Gianmarco kindly reminded, and some methodology and results as an effort of trying to address the question, takeaways, and what we would like to also perform in the future. Q&A, as I said, will be distributed as you like during the talk, and Fabrizio will have me go into that. But without hesitation, let's start with some consideration. MobileNet v2, memory footprint, inference with batch equal to 1, very low amount of memory. But when the training happens with batch 16, the amount of memory needed, the footprint rises at an incredible speed, 35x. And this discrepancy we need to understand, we need to address somehow. Yes, along the years, different workloads have been conceived. Just to name the most famous, some of the well-known ResNet 50, MobileNet v2. And what were the results? The results essentially were a 4 times in excess reduction in terms of parameters, which is important in order to make tiny the model footprint. But the model footprint in one possible embodiment goes in read-only memory. What happened to the random memory, which could even be embedded or even worse, external, with some implication in power consumption. And there was not much improvement in terms of memory occupation between these two networks. The reduction was just 10%, and it was too minimal to really provide evident advantages. So let's go a little bit through backpropagation, try to simplify a couple of passes, forward and backward passes. And we start with activation. So layer by layer, we compute a weighted sum of input tensor multiplied by weights, added by a bias through a nonlinearity of choice. And then layer by layer, we have these very simple mechanisms that go through the inference workload. But then at the end, we need to compute a number of results. First of all, we need to compute the loss again, so the activation of the last layer versus the target versus the ground truth. And then we need to compute the gradient of the loss. Then we need to compute the derivative with respect to the output activations, which here are depicted before the last nonlinearity, and start the chain in order to update the weights. And in fact, in reverse pipeline order, we compute the derivatives of the loss function, and through this product is the Hadamard product, we computed the essential information for the weights update in reverse order. So if let's review this once again with an animation, a very simple forward pipeline. So for each neurons, which are these small circles, we compute the transfer function, as I said before, and then we compute the derivative of the loss function, and then we use it. We use also the derivative of the activations before the nonlinearity in order to, with the Hadamard product, in order to compute in reverse order the derivatives, and then apply the weight updates, so that weights can change during the learning. And where are where are placed these weights? Essentially in RAM memory, because this is the place where to store them. One of, if not the most relevant work in the state of the art that tries to cope with this quite huge problem of memory consumption and therefore memory reduction is MCUNet. MCUNet v3, you know, was the work that tried to limit in a quarter of megabytes the RAM requirement for the visual wake words. And this was the result of a number of key ideas. For example, quantization aware training, quantization aware scaling, so that the learning is performed with integer 8 bits quantization in the loop, and while the backpropagation happens, the quantization noise is the impact of the quantization noise on the weights is mitigated. There are other key important contribution. One in particular is the sparse update. Essentially, if we are able to select offline some parameters that will contribute to reduce the error during the training, the approximation error during the training, then we can save a lot of memory in terms of activation needed to implement the equation I was just showing before. And the results were evident, up to 9 times memory reduction. But still, backpropagation was needed. Now, why are we interested to move away? At least this is my reading. Why we need to move away from backpropagation? A couple of considerations. This is very trivial, I know. When you want to accelerate a workload, you need to offload the CPU, whatever is the CPU, and there are plenty of demonstrations. I don't need to remind you of hardware accelerators and the one for artificial intelligence maybe are just the latest. But the story is always the same, even from the graphic, even from the video decoding, video encoding, and other computational heavy tasks. Simply, unless you want to use hundreds of general purpose CPU, you need to design a very efficient, also in terms of memory communication, hardware acceleration. And if we see what is the current trend about AAIA, essentially AAIA is very populated by devices capable to support inference workloads. And in particular, the hardware that we see around today is really optimized for forward workloads. Forward because the inference is a forward workload. And these solutions are trying to, in different way, to keep very high the ratio between operation and works. So being very efficient in terms of computational density and power saving with respect to many other non-tinyML oriented devices. So the reality is that these are optimized for forward processing. So I think this is the key element to consider. And therefore, the question consequently would be, can we take advantage by the efficiency of this processor in order not only to support inference workloads, but also learning, obviously, by consequence, in a forward fashion. So let's introduce the two algorithms that we concentrated on, and I think they express the state of the art today and the latest efforts in this direction. But before to describe forward and PEPITA, let's share some observation about why we need to focus on a learning workload that is biological plausible. Essentially because our brain learn by modifying the synaptic one by one individual connection between neurons, and this create loops. So we don't know today how the single modifications of these connections are organized in order to achieve a global goal, for example, learning a task. We need that this happens in loop-based fashion, and it seems, because really it's hard to study how the human brain works, it seems that the learning is organized in loops where error signal and credits, therefore how much each synapses contribute to these error signals, are assigned to other synapses in neurons. So on the here you see 3 neurons in a loop, and while on the right this is not a loop between neurons. So as you can imagine very quickly, there are no backward passes here. There are no feedback loops in the sense of meant by the backpropagation. So it's if you allow me in this series of comments, it's evident that our brain doesn't use backpropagation, and for four key reasons. There is no weight symmetry, so there is no back projection, and there is no reuse of weights of the forward pass. The intermediate activation are not stored, so there is no freeze in the neural activity, kind of streaming fashion of information flow between axons and synapses, and then the neuron. There is no global function, but a local function, a local, there is no locality of the loss function in the sense that these signals, as I said, are exchanged from local connections, and therefore the local signals is what they exchange and they use. And there is no update looking mechanism because there is no backward pass, there is no back propagation, and that's the story. And a lot of work has been done in the last 30 years trying to mimic the brain capability of learning. And I highlighted some keywords: learning without feedback, credit assignment to broadcasting of a global error vector error, and deep learning without weight transport, random feedback weights, direct feedback aligned, and so on and so forth. So there have been a considerable effort through the decades, and then at the last, in the last period, two algorithms emerged, one proposed by Geoffrey Hinton and by Giorgia della Ferrera and other co-authors, trying to go beyond the backpropagation. So let's comment a little bit what is forward-forward from Geoffrey Hinton. We process positive and negative data, and therefore there are two forward inference, one for the positive data and one for the negative data, so for positive and negative data. You see that essentially there are the usual equation for inference on layer by layer, neuron by neuron, in a neuron by neuron, layer by layer function. And there are positive weights that will represent updates for each layer independently from the next one. And there is a huge locality, and the same is for the negative. You may see that the activations which are used to modulate the weights are computed for each pass, which means that there is no storage of activation between the two passes. And also activations are normalized when will be communicated at the output of a layer to the next one. There are two variants, one supervised and one unsupervised, with different learning procedures. And the peculiarity of the supervised variants is that for n classes require n passes. And this has an immediate effect on the computational complexity. There is the definition at local level of a goodness function. For example, the sum of the squared activations. This could be one way to define the goodness function. And then the probability for a data to be classified as positive or negative depend by the goodness function. And we need to maximize or minimize this probability in order to match the ground. So once again, in a pictorial animation, forward pass for the positive, the goodness function, the weight of it, and at a layer by layer level. So then normalization, and then we move to the next layer. For example, the multi-layer perceptron pipeline, and for each of them we also compute the activations, then the goodness function, then the modulation of the weights. We normalize the data. We move. What is PEPITA? PEPITA is another forward algorithm, quite different from the previous one, but essentially we have a couple of passes. The standard pass, which is an inference workload, and at the end we compute essentially an error between the output and the ground. And then we modulate the input activation of the pipeline with a random matrix which has a zero mean and small variance. And this is this modulation happens to the activation which are feeding the modulated pass. And then we move forward in the sense that we compute layer by layer activation, and then only at the end the weight updates happen, because essentially by storing the activations computed on the standard pass and the modulated passes, we can modulate the weights. So what does it mean? Likely, it's a fact that we need to store in memory activations from the standard path, and this will have an implication on the memory footprint. While in one supervised fashion, the forward-forward needed to enucleate the complexity for n classes. So these algorithms have drawbacks that we need to quantify. This is a small detail where essentially it's a pictorial representation of how we compute the error at on layer by layer basis in order to then apply the weighting equation. And once again, PEPITA, this is a pictorial representation of PEPITA where we have the standard passes for each layer. At the end, we compute the output, the error with respect to the ground truth. We essentially compute these random matrix, and then we modulate the input, and we start again, and so on and so forth. So having introduced backpropagation, forward-forward, and PEPITA, which are essentially great algorithms, I do recognize backpropagation today is the most accurate way to train an inference, and yet has to be proven that at the same level of quality, forward and PEPITA can be competitive. So this is something still representing a question mark. But before to go into the race, what is the highest accuracy and so on, we were wondering, me and Fabrizio were wondering if it's convenient from a computational complexity and memory footprint apply this algorithm using standard benchmarks which are developed and defined by MLCommons. MLCommons has different working groups. One of these is called Tiny. They define tiny workloads, and today are well established within the industry community to profile any implementation on any processor using them in order to compare apple by apple with apple. Obviously leaving the freedom to everyone to run its own implementation. So by addressing this question, we wanted also to introduce PEPITA, which essentially is an optimization of PEPITA, because PEPITA does need to store intermediate activations, and therefore we want to remove these this storage in order to reduce further the RAM memory, and also profile all these algorithms, the propagation, forward-forward, PEPITA and PEPITA, on these reference well-known benchmarks. So what is PEPITA? Essentially, is like PEPITA has the standard pass, so we have a forward inference, and then we compute the error, and then, as before, we compute this matrix F with zero mean and small variance. So we do apply it, and we modulate the input activation for the next pass. And then we run in parallel standard pass and modulated pass, which are essentially two inference workloads. As you can understand, we essentially duplicated the complexity of the modulated pass. But in such a respect, we save, we recompute dynamically the activations, which are the results of the modulated pass, and therefore we save memory. And as usual, if we save memory, we need to pay something in computational complexity in order to update the weights. So clearly, modulated pass and standard pass are two parallel workloads. So depending on an implementation, one could also consider to avoid the sequential computation, but also parallel computation of these two macro tasks. Therefore, if we try to summarize essentially the learning procedure, BP stands for backpropagation, forward-forward, PEPITA and PEPITA. These are numbers, therefore the forward pass, PEPITA requires 3, backpropagation only 1. Backpropagation requires 1 backward passes, the other 0. The weight updates is doubled with forward-forward, single 1 is equal to 1 for all the elements. The loss function global for backpropagation and PEPITA local, PEPITA and PEPITA is local for the forward-forward. So what is the methodology that we applied? Essentially, let's focus on the MLCommons-Tiny benchmarks. The use cases are keyword spotting, person detection, image classification, 10 classes, anomaly detection, 2 audio type of processing, 2 image-based processing. The topology of the network are defined, and their accuracy in the so-called closed division has been profiled. So that closed division means that essentially you train a floating point workload and then you apply post-training quantization to 8 bits and then you get the TF-Lite file, which in the baseline implementation you can run through TensorFlow Lite Micro runtime on a sample STM32 L4 F5ZI, if I well remember, microcontroller, and you get the baseline. Then all the summation will be against the baseline. Everybody will try to, within a certain margin of accuracy, show fastest speed, so lowest latency and lowest power consumption. The submissions are available. You will see going to the page of MLCommons-Tiny the current state from many industry. So we use that these are benchmarks in order to profile the complexity and the memory footprint. We assumed that the way biases activation are represented in integer 8 bits, the softmax layer still in floating point 32 bits, all the multiply and accumulations, which represent the computational burden of the neural networks, are represented in integer 8 bits. There is no layer memory overwrite, batch normalization is not considered, and we do consider a couple of processors, the Nucleo G4 running 100, STM32 G4 running at 170 MHz, and the H7, STM32H7 at an alpha gigahertz, and therefore we consider the average cycles per Mach and the processor frequency in order to estimate the latency. Results have been cross-checked with the numbers that we can derive using the STM32Cube.ai developer class. Essentially, you get free access to this facility that is developed. You can upload your workload, select a number of boards, and automatically deploy and profile the memory and the execution time without writing any line of C code. And that's the methodology we transparently used to calibrate and to cross-check our estimations. In the complexity analysis, every workload, backpropagation, forward-forward, PEPITA and PEPITA have been broken down in their contributions. And obviously, only forward-forward has a goodness function, which are a normalization, which are being evaluated, as well as only PEPITA and PEPITA as the error process projection workload, which also alter the computation that we are going, the estimation of the complexity that we are going to show. In terms of RAM estimation, we didn't use a sophisticated memory allocator. Essentially, for backpropagation and PEPITA, we, in terms of activations, we added all the buffers needed to store the activation for all layers altogether. For forward-forward, we used the max value of the sum of the activation buffers required by the processing of 2 consecutive layers, and then we added also the input buffer to this computation. And for MLPEPITA, the max value, as I said before, plus the largest activation buffer between 2 consecutive layers. So we have the activation RAM from one side and the total RAM from another. The total RAM not only hosts the activations, but also the memory required to store the weights and biases, because during a learning workload, these will change. And these need to be fastly accessed and written back. Therefore, they stay in RAM and not in flash. So what are the results? Essentially, I will try to simplify, but let me a little bit point you at this number of values. You see essentially the workload for keyword spotting, visual wake word, so person detection, CIFAR10, and anomaly detection. For each of them, we profiled complexity in terms of multiply and accumulation under the assumption I said. The activations, so MAC are in mega, activation in kilobytes. The number of parameters, the ratio of the parameters versus the activation, and the RAM, and the total RAM as addition of the previous 2 values, the activation and the parameters. In green, you see the reference value. For example, the reference value for backpropagation on keyword spotting on the MAC is 7.7 million. Forward required 43% more computational complexity. PEPITA 4%, MLPEPITA 39%. And we can go through each of them. Activations. The lowest memory is required by forward. And then there are at least 253% more needs from the backpropagation, and PEPITA only 33% by MLPEPITA. In terms of activations, in terms of parameters by activation, you may notice on the right for anomaly detection a real high ratio between parameters and activation, because this model is really rich in terms of parameters, and this will have an impact on the final gain in terms of RAM. For example, for keyword spotting, 43 kilobytes, an increase by 120% by backpropagation and PEPITA, and only 70% by MLPEPITA. In the case of anomaly detection on the right, 267 kilobytes for forward and MLPEPITA, and only a marginal increase in terms of RAM due to PEPITA and backpropagation. But this is due to the impact of the weights, which are quite heavy in terms of footprint. But if we concentrate only on the activations, you see that really forward and MLPEPITA require only 1.4 kilobytes, while 60% increase due to backpropagation. So I will not enter on the others, but essentially, if we average all these results for the CNN, because keyword spotting, visual wake word, and CIFAR10 are based on convolutional forward topologies, while the anomaly detection, which is an autoencoder, is fully connected, what we see is that PEPITA requires only, with respect to backpropagation, only 3% in terms of computational complexity. Activation 0%, and RAM 0%. But there is a huge decrease in terms of RAM, in terms of activation, thanks to MLPEPITA and forward. While the total RAM is marginally changed with respect to backpropagation on the autoencoder, but once again, forward and MLPEPITA has a nearly 40% decrease in terms of memory, while PEPITA, as expected, is on par than the propagation. Let's go to the inference. On the inference, we notice immediately, I go through the average because essentially same comments as before applies, that let's go to the average, and on the average, you immediately notice a huge workload due to the forward-forward. And this is 700% due to the number of classes that, for example, we experience on CFAT10 and on keyword spotting, less on visual wake word, but really this is, let's say, the cons which are associated as far as supervised learning is concerned on multi-class problems due to forward-forward. The complexity is really increased too much, as well as the RAM, while for the others is as essentially any other inference work. In terms of latency, I just recall that we tried a couple of processors, which are the STM32H7 are 550 megahertz, and the Nucleo G400, a low-end microcontroller, 170 megahertz. As I said, these are estimated values, so these values are not coming from a C implementation on the microcontroller. On the other side, have been calibrated through profiling of similar workloads using the developer cloud I was mentioning, and so we carefully calibrated the cycle per Mach that we used to derive these numbers. And so a couple of rows, training in millisecond, inference in millisecond. In green, the execution time estimated for propagation. So, for example, on keyword spotting, we have 42 milliseconds of workload for training on H7 and 200 milliseconds on the G4. Forward increased by 40%, nearly 40% as well as PEPITA. So this is what we take. PEPITA, clearly, PEI, marginally more than backpropagation. On the inference, forward pays, as expected before, all the enuplication, let's say, of the complexity on a class problem, while the estimation essentially is on par between backpropagation, PEPITA, and PEPITA. So what are the key takeaways at this point in time after all these numbers? Essentially, let's start from the learning and let's focus on forward and PEPITA. So there was, with respect to backpropagation, an activation buffer storage reduction average 40 to 65%, at the price of more computational complexity, 40 to 100%. PEPITA, same memory as backpropagation, with a marginal increase in terms of complexity for the CNN topologies in the tiny benchmark, while on fully connected, close to 70%. So the total RAM reduction is very noticeable if the topology have a quite low ratio between the number of parameters and therefore their footprint and the activation footprint. But and in fact, it was really on a very low on the keyword spotting depth separable CNN 0.3, and the RAM reduction was, let's say, quite 100%. While on the inference, we have the same complexity between PEPITA and backpropagation because there is only one forward path. But unfortunately, for supervised forward, the computational is really increased, as I said many times. So what should we remember out of this work is that PEPITA can reduce really the memory about 33% for the considered convolutional neural network, and marginally for the for the fully connected topology, at the expenses of a third more multiply and accumulate. The inference complexity remains unchanged. If you want to learn more about how these estimations were done, Fabrizio made available a GitHub repository where there are descriptions and also the way, the methodology we used to compute this number. So we are happy to be challenged on this estimation. If you want to take a look at it and reports, any comment, we will be happy to consider them. So please, at your earliest convenience, have a look at them and report any discrepancy you may consider worth to be reported. So I think Fabrizio already answered a lot of questions, but if you have others, don't hesitate to post them now or even later on at your early convenience. Me and Fabrizio can be contacted. You can write to me and then Fabrizio will address any future question. Having said that, I am very grateful for your time. And I hope that this work was interesting. As I said, we need, I'm really convinced we need to provide and to devote efforts to go beyond the backpropagation. And maybe adopting forward architectures, forward learning architecture, maybe we can even exploit at best the current topology, the current hardware accelerators, even if they were not meant for learning. So I think is also, this is another good reason to consider a departure from backpropagation. Thanks a lot.
Thanks a lot, Danilo, for this brilliant presentation. I did not have any doubts, honestly, for the level of details and the technical things shared. So it's absolutely, was absolutely great. And by the way, I want to thank also Fabrizio, who actually replied to most of the questions that we had in the Q&A box. So, why don't we start from a Q&A box, from the question that we have there. So slide 48, what 100% reduction means? Is it like no memory required at all?
No, but please, Fabrizio, come on audio so that you can also try to... So the slide was 48.
Yes.
Feel free to share your screen, by the way, Danilo. Feel free to share your screen.
So essentially the question is in slide 48, we had a reduction of 100%. What does it mean? We zeroed the complexity?
No, not at all, not at all. Could you please, Danilo, go to the, for the DSCNN, it's 0.3, and RAM reduction is around 100% with respect to backpropagation, of course.
Maybe I can go to back
to the slide before, so we can better refer to the
this one.
Well, yes, in the DSCNN scenario, plus 120%. Yeah, they were compared, I think, not with respect to backpropagation. The decrease in RAM, it is actually for CNN in average is 41% and 43%. Actually, I don't get the question. I hope that maybe now it is clearer to which values to refer. So on CNN, on average, the total RAM reduction is about 41% for FF. PEPITA leaves it unvaried, and PEPITA is about a third. So 43% memory total RAM reduction, total RAM, including also parameters. And on the DSCNN, we see that the values are referred to FF, as FF reduces the memory the most between BP, PEPITA, and PEPITA. And so the values which are reported in the table, 253% increase, is referred to the memory of forward-forward regarding activations. Regarding RAM, it is still forward-forward. I hope to have answered your question.
Many thanks, Fabrizio, for answering the question. So I'm going off like this. Okay, done. Probably there were some interesting questions that you have already answered in the Q&A box that probably are worth sharing with the audience. One is about the availability of this forward work. Is this work still experimental, or there any open source project that people can refer to?
Well, actually on GitHub, you can find a lot of implementations of forward and on forward on PyTorch and TensorFlow. And actually, if you visit the site of Hinton, the website of University of Toronto, where Hinton teaches, you can find the MATLAB code originally used in the original paper of Hinton regarding forward. About PEPITA, there is the implementation in PyTorch on GitHub written directly by Georgia.
Okay. And are these are you aware if these can so are these for cloud forward training or for edge forward training?
The models on which both forward and PEPITA were evaluated in the original paper, so the models that were used in the GitHub code, are not models suited for the edge, are large models evaluated on datasets which are not the MLCommons-Tiny, which do not belong to the MLCommons-Tiny benchmarks. So no.
Here there is another question about the forward algorithm. So the forward algorithm needs n passes for a supervised classification. Does it not increase the inference cost by a factor of n? I think this has been already addressed in the presentation, but please, if you can comment on this.
Yes, basically, forward performs at inference n passes, where n is the number of classes in the classification scenario. So it increases the inference by n, as the inference of backpropagation, PEPITA and PEPITA is the same and consists in one forward pass, as Danilo has said. Instead, on the anomaly detection case, you basically need only one forward pass. So there is no actual increase in complexity during it.
Okay. Thanks.
Okay.
There is an additional comment on this. It is not just linear, the number of classes, because there are further, I'm sharing the table, there are further algorithms like the evaluation of the goodness function, which essentially depend on the definition of the goodness function. For example, the squared, the activation squared, and then added all together, which is quite complex depending on the footprint of the activation that happens at local level, and as well the normalization. So these are extra complexity that essentially are on top of the linear increase of the forward complexity in a superfine n classes problem, which are very peculiar to forward. Then this type of goodness function was really an example, in the sense that Hinton encouraged also future research on other implementation of the goodness function. This is something which essentially further complicate the complexity of computational complexity.
So I have one consideration more than a question, actually. Is about forward at the edge. I mean, if we consider a microcontroller, if we perform the forward algorithm for, let's say, improving the accuracy of the model, I suspect the limitation, apart from the extra memory that is required, is also the fact that the weights in this scenario cannot be stored in Flash, right? So do you expect this to be a limiting factor for deploying this kind of algorithm or on-device learning algorithms at the edge, in particular for microcontrollers?
Sure. Let me go back a little bit to the forward definition. So as you can see, essentially, you see that weight update happens, first of all, the update is local. And then there is a different update between the positive and the negative passive. Now, we didn't study the best way to store in which type of memory the weights, but essentially the locality and essentially the avoidance of immediate reuse in the next layer may open the opportunity to store them in flash memory while the training happens. But as I said, it's a very preliminary consideration, depending really on the embodiment. I think the real issue or the real question mark on the applicability of forward to tiny workloads, to tiny neural network for edge AI implementation is that this excessive complexity for supervised learning. And this poses a big question mark on the applicability of results. Not speaking about the accuracy. Essentially, this is an unknown factor at this point.
Many thanks for clarifying, Danilo. So, any other questions before we start with the end of this presentation? We are going to run. If not, so I want to thank Danilo again and Fabrizio for the crucial support, because Fabrizio replied to more than, I think, 14 questions in the Q&A box. So thanks a lot for that. Perfect. So again, thank you, Danilo and Fabrizio, for your time and for preparing, this presentation, because we have a lot of slides with a lot of technical details. I think this was absolutely beneficial for the audience. I learned quite a lot, actually. So thanks. We're approaching the end of this presentation, and again, a very and we need to thank our strategic partners for making this event possible. So I'm going to start with the executive strategic partners: Qualcomm AI Research, Synchant, the Platinum strategic partners, Sony, the Gold strategic partners, Analog Devices, ARM, Edge Impulse, Infineon, Inotera, Microsoft, Renesas, STMicroelectronics, Synaptics, and here the silver strategic partners, so AZIP, Arduino, BrainChip, Efficient, Greenwaves, Gravity, HiMax, IBM, ImageMob, Note AI, NXP, Pauling Technology, Kixo, Schneider Electric, SensiML, Silicon Labs, and TDK. And with this slide, we are going to close this brilliant presentation. And I'm looking forward to attending the next session, the next tinyML talk.